Hello, good morning, good afternoon, depending of where in the world you are watching. Thank you for joining us today in the A4Q World Congress. My name is Andrea. Today we have a very special guest with us, Alessandro Collino, as you can see already. So I just want to give you a very quick introduction of Alessandro. Not going to take too much of his time because he has a great presentation ahead of you for everyone watching. So he graduated in computer engineering at the Politecnico of Milano, and with over 17 years of experience distributed in various sectors. His main interests concern the wide area of software testing. He currently works within the technical director and academy apartments at Alten Italia, and also co-founder and active member of ITA STQB, the Italian chapter of the ISTQB. So as you can imagine, you have a great speaker ahead of you. So I'm not going to take too much of your time. I'm going to pass this on to Alessandro and share his presentation.
Okay. Thank you very much, Andrea. So good morning. As Andrea already said, I'm currently working as a software testing specialist within the technical direction and at Alten Italy. I'm also a trainer for ISTQB. I have been working in Alten Italy for 10 years. And I'm also an active member of the ISTQB and co-founder of the Italian Software Testing Qualification Board. So let's start. Let's start with my presentation because let's say the topic is really huge, and basically. This is the title, okay? Testing strategies for microservices-based web application in a DevOps framework. Let's say, okay, of course, first of all, thank you for being here at this session. This is the agenda. Of course, first of all, the topic is really vast. So we must first define the scope. In this figure, I have represented the sub-dimensions of information technology and also their evolution over time. For example, we see here that the development process has evolved from sequential models to cultures such as Agile and DevOps, which are very popular today. Application architecture has also evolved from monoliths before to entire architectures later. Entire architecture are, of course, still quite monolithic, to increasingly distributed and scalable architecture, such as service-oriented architectures and microservices architecture. Remember that microservices should be loosely coupled so that they can be actually developed, tested, deployed, and also scaled independently. Deployment and packaging have also evolved from physical machines to, let's say, to virtual machines first and to containers later. Remember that both virtual machines and containers implement virtualization techniques. Basically, virtual machines implements hardware-level virtualization, while containers implement operating system-level virtualization. Hardware-level virtualization is very flexible, but is also very heavy in terms of resources, and the flexibility of hardware-level virtualization is not always required. And often, let's say, operating system-level virtualization of containers is a better option. Containers can be adopted when their operating system is compatible with the host operating system, that is usually Unix or Linux, but there are also nowadays implementation for Windows, and provide a strong degree of isolation, okay, that is comparable to that of virtual machines, using only a small amount of the resources on the host system. So containers are very useful because are a very lightweight, okay? They are much smaller than virtual machine, let's say 1/10, 1/100th of the size of a virtual machine, and because they do not require the operating system spin-up time associated with a virtual machine, they are much more efficient at initialization. Overall, container can start in second or even millisecond in some cases, much faster than a virtual machine. Of course, a microservices architecture does not prescribe the use of containers. For example, as you probably know, Netflix, for example, runs its entire microservices-based offering on Amazon Web Services, okay, using the corresponding instances, okay, the so-called EC2 instances. However, most organizations that move to microservices architecture find containers a very congenial and effective and efficient way to implement their application. Okay, also application infrastructure has evolved. Nowadays, cloud computing is very popular, okay, with its service model. Also, storage and storage as a service has evolved, and storage as a service can be seen as a, let's say, as a cloud service model, actually. And let's say that overall, this evolution enables performing the so-called shift left, okay, from a testing perspective. So let's say that the testing strategy we will define for this application, for these web applications, must take also advantage of this principle, okay? Of course, there are many challenges involved. So our goal is to describe these challenges, okay, for defining an effective continuous testing strategy for these for microservices-based web application within DevOps framework, and of course, how to deal with them. Of course, there are several aspects of a testing strategy. Three fundamental aspects that we will address here in this presentation are the test levels, the test environments, and the integration with the continuous integration and delivery pipelines for continuous testing, which perform the execution of automated tests at the various test level in the corresponding test environments. Our testing strategy primarily focuses on functional testing. So let's say that this is here you can see a DevOps framework. Of course, continuous integration and test automation are fundamental agile practices, and DevOps, simplifying, adds two more practices: continuous delivery or deployment and infrastructure as code. So let's say that such practices belong to the dev side, if you want, of a DevOps framework and allow supporting a continuous testing strategy. Continuous delivery requires continuous integration, and continuous deployment takes continuous delivery a step further, with the notion that every change can be automatically deployed into production. Not that I said deployed and not released, because as you probably know, a DevOps framework usually separates the two concepts. And this separation is very important also because it leads to a new set of practices associated with the ops side of the DevOps framework. Those practices, let's say, come from, let's say, are in production. Testing in production are rapidly evolving. Some of these practices, for example, traffic shadowing, tab compare, and come from chaos engineering, which is a relatively new discipline. These practices on the ops side of the DevOps framework are not addressed in this session, but please consider them in an overall testing strategy. If you are interested to the topic, they represent indeed important practices that could extend our testing strategy by adding further quality gates in production before actually releasing the product. Indeed, in this session, our testing strategy focuses on the quality gates associated with the test level on the dev side, mainly. So this, in terms of the, this is the scope in terms of the DevOps framework. Let's see now the scope in terms of the application. We will basically consider web application like this one, a front end with a web UI, a backend with microservices running in containers, okay, our artifacts, within a cluster, because of course, usually microservices, our artifacts, our microservices within the containers must be orchestrated. So we can assume to use, for example, Kubernetes, that is a cluster as a service, or even products such as OpenShift, that is a platform as a service that internally uses Kubernetes. And so the front end, the back end, and let's say a reverse proxy that acts as a mediator between the front end and the back end, and let's say that performs the static routing of the request coming from the front end to the back end. We could also use, of course, an API gateway, but it's not especially relevant for our purposes. What is relevant is to remember that the communication between the microservices within the backend can be synchronous or asynchronous, okay? Basically, let's say we refer to REST for synchronous communication. So basically, these are often implemented, the APIs as of the microservices as RESTful APIs that use HTTP as a transport layer, as you know. And so a very traditional, let's say, request response. And also asynchronous communication is very important. And asynchronous communication can be implemented, for example, with message passing. Let's say, in this case, microservices communicates by exchanging messages via a queue. In this case, we could refer to different message brokers, for example, Kafka, RabbitMQ, ActiveMQ, JMS, and so on. Let's say that the problem here, as we will see, is that the protocol used to interact with these message brokers are different from HTTP and run on top of TCP. This could be a problem when creating mocks. Maybe, for the sake of brevity, I will use the terms message broker and message queue interchangeably. Of course, the message queue is the data structure, while the message broker is a component, a software component that manages queue. But this is a detail. So these are which are the main challenges, okay, in our case, in this scenario. Let's say that there are, of course, many technical challenges. First of all, high variability in patterns, okay? For example, sometimes you can see that microservices use a choreography mechanism, while in other situations they use traditional orchestration. And remember that microservices architectures favors service choreography over service orchestration, because primarily, as we said before, the architecture topology lacks a centralized mediator, a centralized middleware component. However, you can see different implementation even in terms of choreography and orchestration. Another important design decision, refers to the ownership model. Let's say, so what is the relationship between our microservices in the backend and our teams in terms of ownership? This is often crucial for defining an effective testing strategy. Because, as you probably know, one approach is a shared ownership model where, let's say, multiple teams basically can work on each microservice as needed. And this is basically, so each team may be responsible for implementing features that span multiple microservices. This approach aligns teams with the user experience, but on the other end, also it increases the amount of coordination needed between the different teams. Another approach, which I have seen more often implemented, is, let's say, a microservice ownership model that increases team autonomy and loose coupling. In this case, the team owns a code base which they deploy as one of more microservices. As a result, the team can freely develop, test, and deploy and scale its services. So basically, in this case, the interaction between the team is focused on negotiating APIs. Another design decision concern, of course, for example, data management and so on. There are many, many different patterns that can be applied in a microservices architecture. Another important point for test automation is determining the test orchestration. Let's say that basically the integration of automated tests for the various test levels into a continuous integration and delivery pipeline can basically take place in two different ways. First, having, let's say, the pipeline as a master test orchestrator. In this case, the pipeline is responsible for orchestrating all the activities foreseen for each test level. So the creation of the test environment that applies only to temporary test environment, the creation of the system test, the test harness, the execution of automated test, logging and reporting, the destruction, okay, the tear down of the test environment, and so on. The second option is having a test automation framework that acts as a master test orchestrator. In this case, the orchestration of all the activities foreseen for each test level is, let's say, delegated to a test automation framework. This is usually a situation in which the test automation framework becomes the master of the orchestration for all the activity planned for the test level, and the pipeline basically becomes a slave to that orchestration. Usually, this second option is usually the best one for several reasons that we will describe. Another important fundamental point is removing non-determinism, okay? Because as we know, as the test scope increases, so too do the number of moving parts. And the more moving parts, the less deterministic our automated test exercising the system are. So these moving parts can introduce false positive, basically. And and this leads to non-deterministic behavior, okay? And sometimes the automated tests are, let's say, called the so-called flaky test. They pass, sometimes they pass, sometimes they fail, even if the system always works correctly. Of course, non-determinism is due to the fact that the system is distributed, okay? So let's say that non-determinism is a problem present in all distributed architectures. In our microservices architecture, we will especially deal with this problem, of course, when integrating microservices. There are also several organizational issues, even we are not especially interested to them in this session. And one of them is often the lack of technical tester and test automation engineer. Indeed, as we will see, defining and implementing a continuous testing strategy in this framework definitely requires more technical people. So basically, let's say that let's say that in the following, we will assume that all our microservices coordinate with each other and that they are loosely coupled so that they can be, let's say, developed, tested, deployed, and also, let's say, scaled independently in this case. Based on the patterns adopted, okay, this is not always the case. Indeed, not only functional coupling, but also runtime coupling, okay, can occur. Such coupling will make the build, of course, more, for the backend, more monolithic. This means that our builds could consist of a set of coupled microservices, but apart of that, of course, our testing strategy will still be applicable. So, how to start for defining our testing strategy? This is the scope. How to start? If you look around, you will find several reference models for testing strategies, not only the well-known test pyramid, but also the test honeycomb from Spotify, the test funnel, and so on. All of these models are valid and differ from each other in terms of test level, relative size of test levels, and on whether they address manual testing and testing in production. Remember, the ops side of the DevOps framework. The problem with this model is, of course, that the terms they use mean different things to different people. However, in the scope we have defined, the test pyramid is more sequential and has a very solid foundation. Let's say, of course, as we know, this is a test pyramid, and let's focus on the UI test for a moment, okay? As you know, these tests are usually end-to-end tests activated at the front-end level, which in our case is Web UI. They cover a lot of production code and provide a high degree of confidence that the code being tested actually will work in production. But this increased scope comes with several downsides, as you know, probably. For example, the first downside is that this test must run on a fully integrated test environment, the so-called pre-production or staging environment, that must be very close to production environment, and that is usually very expensive to maintain. Moreover, being this environment fully integrated, of course, this automatic end-to-end test tend to be flaky tests, okay, as we said before. Another important downside is that these tests are also very brittle, okay, even if we can, of course, adopt a page object pattern, keyword-driven approaches, and so on. However, this test will always require significant effort in terms of maintenance. Another downside is that these tests are also very, very slow. So running many of them to get early feedback, frequent and early feedback, running them on the continuous integration delivery pipeline could not be feasible, okay? So, of course, the test pyramid is only a reference model that needs to be adapted to the specific context. What is our context? Based on our assumption, all our microservices are loosely coupled, okay? So, in this case, teams interacted to negotiate APIs. In this case, okay, with this assumption, with this pattern, for example, microservices are like components that at a certain point need to be integrated. It is like having component teams. So microservice integration testing is necessary. But we also know that agile development favors feature teams over component teams. So how to deal with this situation? Let's clarify better this point for a moment. For example, if we have a microservice, micro S1, for example, this is the team owner of micro S1. At microservice level, the team is basically a feature team, okay? And being a feature team, the development of the feature for micro S1 is cross-unit, okay? If I refer to the unit within the microservices. However, the overall application results from the integration of several microservices, each of which is owned by a feature teams. This means that teams are feature teams at the level of the microservices they own, but they are component teams at the level of the overall application. So, in this case, of course, we need a microservice integration level in our test pyramid. And but the main question is, can we manage this test level with traditional approaches to integration testing? No, because this would require a dedicated stage, okay, for integration, and so this solution is not compatible with effective continuous testing strategies. We need modern approaches to integration testing, okay? So basically, here you can see on the left, a test pyramid for a system of system in sequential models. with component teams on one side with traditional approaches to integration, and on the right side you can find the test pyramid adapted to our context with a microservice integration test level, where there are feature teams at microservice level and component teams at application level. And in this case, as we will see, we need a more modern approach to integration. So, of course, this is the typical situation, okay? For each test level, we need to identify, for each of the 4 test levels that we specified here, we need to identify, let's say, the corresponding test environment. In this case, for example, this picture refers to a Git flow, okay? That is a very well-known branching model for Git. The teams, which are featured teams at microservice level, often use. Without entering in the details of the Git flow, at a certain point, a change to a microservice triggers its continuous integration and delivery pipeline, where for each test level, the automated tests are executed in their corresponding test environment. Let's say that, for example, we can use a table like this in order to describe the test environments at the different test levels, okay? Let's say that these test environments can be described in terms of their scope, okay? Is the test environment dedicated to a component, so for example, to our microservice, or shared between different microservices? In terms also of lifetime, is the test environment temporary or permanent? Also in terms of the infrastructural support, okay, maybe the test environment is light, so it is not necessary to have a Kubernetes cluster to manage the different artifacts, or heavy, okay, if the test environment requires also a Kubernetes cluster. Of course, also, let's say, other field in this table, for example, the composition in terms of the application infrastructural components, and also the test automation used within the test automation framework. This is a schematic representation of a microservice. There are one or more units implementing the business logic, one or more units implementing data persistence, okay, for example, for accessing the databases, and one or more units dedicated to the synchronous and asynchronous communication, okay, both inbound and outbound. Let's say that the first test level at the bottom of our test pyramid is the so-called unit testing and unit integration testing that considers together 2 logically separated test levels of unit testing and unit integration testing. In this case, the units are the units within the microservice. So basically, these units represented here. Let's say that this merge at the bottom of the pyramid is justified by the fact that the unit test and the unit integration test have almost the same characteristics, are carried out in the same environments, and are a responsibility of the developers. Let's say that basically, okay, these tests are very fast, very deterministic, atomic, isolated, fully automated, written in the same language of the production code, and so on. Let's say that also usually at the unit test level, the better solution is to test with individual unit test the business logic and these 2 components inbound that manages communication, inbound communication toward the microservice. After that, we have the unit integration test level. Unit integration test also needs to be deterministic in providing feedback. And in this case, it is advisable to eliminate all those network interactions that could slow them down and or make them fail, of course. Timeouts, service interruption, and so on. So in this case, the recommendation to test the remaining 3 units, okay, so the DB driver and also the units that are responsible to manage the communication, the outbound communication, usually can be tested locally through the use of in-memory databases or internal mocks. However, okay, let's say these are still, this is still a test level, okay, which is basically responsible of the developers. The next test level, okay, is the so-called microservice integration test level. In this case, this test level aims at testing the correct behavior of the entire microservice in isolation, with the microservice running in the container, of course. Okay, we are testing the artifact. At this level, so the focus is on those defects that manifest themselves as the overall interaction of the units inside the microservices when such microservice is running in its container. So while the previous test level is the sole responsibility of the developer usually, this test level is usually also the first in which testers are involved. In this case, this is basically API testing, okay? This is a test level that requires API testing. So in this case, the automated tests are quite fast, okay? Deterministic, fully automated, and in this case, written at API level, okay? For example, with SOAP UI, on Postman, okay? There are many tools. But there is nothing special, nothing new, okay? It is basically API testing. In this case, of course, mocks of microservice dependencies, so microservices in queues, are external. In this case, the test environment, as you can see, is dedicated, temporary, and light. Okay, it must not include any Kubernetes infrastructure. We just need to deploy the artifact on a single machine, the container, through the continuous integration and delivery process. But of course, let's move now to the level of microservice integration testing. This is by far the most important test level. Indeed, the bigger complexity, as you know, in a microservices architecture is not within the individual microservices, okay, but in how they interact with others. As I told you before, traditional approaches to component integration testing usually focus on the so-called broad integration. This means that these approaches consider all the components, in our case, all the microservices within the backend, to be integrated and determine whether all these components correctly communicate to each other, requiring them to actually communicate to each other. Okay? For example, here, a few approaches described in the ISTQB syllabi are shown. What happens with these approaches when a change to a microservice occurs? Let's say that the test environment for the microservice integration test level, in this case, would consist of the new version for the microservice being changed and all the other microservices, of course, in their latest build. Microservice integration test would test the correct interaction between all these microservices. This, of course, would result in all the continuous integration and delivery pipelines associated with our microservices having to manage heavy test environments and running a huge number of microservice integration tests for every single change. This is not feasible, and so we need more modern approaches to integration testing. Basically, basic modern approaches to integration testing, often referred to as narrow or local integration testing approaches, focus on two aspects. First, limit the scope of the integration. They are narrow, they are local. Not all the components are considered in the integration, but only the consumers and the producer of the microservice being tested. Second, determine whether all these components correctly communicate to each other without requiring them to actually communicate to each other. And this is extremely important in order to remove non-determinism. For example, let's see this case, okay? We have three components, X, Y, and Z, with the two specified dependencies. With a traditional broad global integration test approaches, all the actual components are needed, and integration tests determine whether, possibly incrementally, as we know, these three components correctly talk to each other, and this test so basically exercise the two dependencies on the actual components. With the more modern approaches, okay, to integration testing, for each dependency, okay, so we have two dependency here. For each dependency, two sets of tests are implemented. Basically, a set of functional integration tests, okay, not between the component and its dependency, but between the component and a virtual implementation of its dependency, okay? Basically, a mock. But this is not enough in this case. Of course, we also need a set of, let's call, interface tests aimed at ensuring that the behavior of the interface for the virtualized component, okay, for the that represent dependency, is the same as the actual external component. So basically, we can identify for each dependency two set of tests. So what is the situation in this case? Let's consider a generic microservice, micro S1, with n consumer and m producer, and a change on micro S1. Micro S1 is, of course, is consumer of m producer, and therefore, as a team owner for micro S1, we'll have to write m test suites of the functional integration group, one for each producer. And of course, we need also to distribute these tests to the producer, because the producer will execute them on their pipelines, okay? These test suites will be executed by micro S1 at every change. However, micro S1 is also a producer for n consumers, and therefore, again, as a team owner of micro S1, we will also have to write n test suites of the interface group, one for each consumer. These test suites will be executed by the micro S1 pipeline at every change. If one of these test suites fails, okay, you cannot say that the build is broken, okay? You can only say that the interface, okay, this test failed, but in this case, you must also launch the test suite of the functional integration group written by the team owner or the corresponding consumer, okay, which will have been previously distributed to the group owner of micro S1. Only if also this suite fails, then the build, okay, can be actually considered broken. Otherwise, the pipeline will continue the execution of the test suite of the interface group for the next consumer. So this is the workflow, okay? So basically, if there is a change on micro S1, we must first run the M functional integration test suite, one for each producer, okay? If they pass, okay, if something fails, the build is broken. If they pass, then we must start with the n consumers. And so for the first consumer, we need to run the interface test suite, okay? If these basically fail, okay, in this case, as I told you, we cannot consider the build broken. We must run before the functional integration test suite, that is more time consuming, the interface test suite provided by the first consumer. In this case, if this test suite fails, then we can consider the build broken. Okay, this is the workflow for the first consumer, and so on for the second consumer, and for the remaining consumer. Okay, I've also specified here the ownership. Let's say that, as you can see in this, with this approach, the test environment for microservice integration testing is again temporary, okay, and lightweight, very light from this perspective, because it just needs the microservice being tested and its consumer in their latest build. Okay, so we don't even need eventually the having Kubernetes. So let's say that basically these microservice integration tests are usually implemented as contract tests. Okay, this is sometimes referred to as contract testing. Clearly, this technique and these approaches, this workflow, can be implemented by investing in communication and collaboration mechanisms between the team owners of the microservices involved. However, there are also dedicated frameworks such as Pact and Spring Cloud Contract, and usually, okay, let's say their use is recommended. Both are open source, and let's say Pact can be used can support several languages, so Java, Ruby, Python, JavaScript, while Spring Cloud Contract basically can be used only for JVM-based project. What is the point here? Let's say that the point is that with this approach, we are able, okay, to determine whether microservices interact correctly without making them interact. And we are able to write automated tests, okay, in the form of contract tests that are independent, fast, easy to maintain, and also deterministic. That means not flaky, okay? These tests are very, very suitable, okay, with to work with our framework. For example, for asynchronous REST interactions, okay, so request response, basically two sets are produced, okay, a consumer side test and provider side test. What is a contract, okay, for implementing these automated tests? Basically, let's say that a contract defines the expected interaction between the request and the response. These interactions represent the contract between consumer and the producer. Basically, the contract registered on the first test set, so on the consumer side, the consumer against a provider mock, are used also on the second test set, so on the provider side. And of course, this contract can be shared via file systems or via commit on a Git repository, or there are also dedicated brokers within the framework, okay? For example, in Pact, okay? In Pact, for example, these contracts are called pacts, the name of the tool, Pact. A pact is basically a contract within the Pact framework. Okay, let's say, good, this is for a synchronous REST interaction. And in the case of an asynchronous interaction, the problem seems more complex because, as I told you before, in a synchronous REST interaction, everything communicates at HTTP level, where it is easy to create mocks, okay? So the provider mocks, the consumer mock are very, very easy to create. While communication with the message brokers, okay, takes place usually via binary protocols over TCP, which makes mock creation much more complex. However, and this is very important, a contract or a pact, if you are using pact, pact framework, abstracts from the technology used. Okay, so whether you are using a synchronous REST or an asynchronous interaction, okay, so with Kafka, Message Broker, RabbitMQ, JMS, and so on, you always have the two sides of the contract, the consumer and the producer. Let's say that, of course, in case of a publish, subscribe, asynchronous communication, the contract is different, okay? In this case, the goal is to ensure that the message producer generates a correctly formatted message and that the consumer is able to consume it. It is, therefore, not necessary to use the actual message broker. What changes with respect to the synchronous interaction is simply the format of the contract. In this case, with a synchronous interaction, the contract defines the, let's say, the interactions in terms of request and response. In this case, the contract must capture expectations that refer to messages, okay, to events, okay, and these indeed are also called message contracts, okay, so special contracts. For example, these are indeed called message pacts in pact. In pact, usually pacts, so the contracts are expressed in JSON, okay, while Spring Cloud Contract has its own contract definition language based on Groovy, YAML, Java, and Kotlin. And of course, at the end, let's say there are the integration tests. Okay, so the next step will be the integration testing between the backend and the front end as part of the so-called end-to-end test. Let's say that such testing is often managed with broad integration approaches. Unfortunately, as we already know, this inevitably leads to the same issues previously described for the backend. However, we could potentially apply the integration to the integration testing between the backend and the front end, the same reasoning we applied to the integration testing between the microservices to make the test strategies continuous even for end-to-end tests. Of course, because this is always a problem, because of course, in this case, if we decide to manage end-to-end test with a traditional approach, of course, we need let's say, a dedicated, okay, test environment, and also the pipelines on the individual components for the application code and the pipeline for the Kubernetes infrastructure will have to synchronize, okay? So this environment could therefore potentially become a bottleneck, okay? So, of course, this combined with the characteristic of end-to-end test, brittle, flaky, slow, and so on, leads to the conclusion that it is necessary to reduce this test, if you want to do them, as much as possible, okay? Basically, this test should be limited to exercising via the front end all the microservices at least once to be confident about the infrastructure and focus on the most critical use cases, as the business logic in itself must have already been tested at previous levels. Of course, here you can use, for example, Selenium, or for example, if you are using Angular, you can use Protractor. There are modern, let's say, test automation framework for the front end, like Codecept.js, and many, many more. This is the traditional domain of the, let's say, web browser automation, basically, okay? Okay. So let's finish. As you can see, there are several considerations about this testing strategy. The most important is, of course, about microservice integration testing. So if you are interested, you can consider these further topics. Examine how to efficiently and effectively use the frameworks, so basically Pact or Spring Cloud Contract, for implementing contract testing in especially the workflow we described, okay? another important point of the testing strategy is how to extend our testing strategy with non-functional tests for performance and fault tolerance, for example, okay, which are both really, really important in this context. And of course, how to extend the test strategy to the ops side, okay, of the DevOps framework in order to add further quality gates associated with the ops side of the DevOps framework, okay? So the so-called testing in production. Okay, so let's say that, okay, maybe, okay, I don't know if there are oh, sorry, this is quite, I'm in the dark web right now.
Thank you very much, Alessandro. Such an interesting presentation. We got some great feedback as well. We are quite tight on time. I probably would take one of the questions that people put over here, but just to let everyone know that Alessandro, it is going to be in the Congress Hall area. So I have already put the comments in the to the link in the comment section. So if you do have any questions that we did not get a chance to answer for you today in the live version, please go to the Congress Hall area and you will be able to find Alessandro as well to ask any more questions. So I'm going to put just a question here on screen, just 1 minute. Here you go. So from Edgar, we have, if we're automating a microservice that has connection to the database, where should we store credentials for DB connection, or we just mocked DB data?
Okay, these are good questions. It's not complicated. It's not easy to answer because we need several hypotheses on how to manage, okay, the data. Okay, but so maybe I can contact Edgar later so that we can discuss about on this topic, because I need maybe I should have another slide that can be very effective to explain this issue. Okay.
Great. Thank you so much for that, Alessandro. So in that case, Edgar, I would recommend to you to go to the Congress Hall area. I have put the link already in the description. I also have put the Congress website link on screen. So if you go there, you're also able to go to the Congress Hall area and look for Alessandro. I've just put a couple of positive feedbacks that we have received. Great talk. Thank you so much from Clarita Ramos. I believe she said earlier she was watching from Italy. So thank you so much for that. And once again, thank you so much for the great presentation. Very informative as well. I can see a lot of people in groups really, really liked it. And I think quite a few people is going to go to the Congress Hall area to meet with you and have a little bit more of a chat. That is going to be it for today. We do have another presentation started, 2 other presentations started in less than 10 minutes. So I also encourage you to check them out afterwards, and you can go simultaneously to the Congress Hall area. Thank you so much, everyone, and have a very good evening, depending on where you're watching. Take care.
Thank you, Andrea. Thank you. Bye.